Welcome back to Math 111, Elementary Statistics at Georgetown College. This is part 3 of Chapter 4 on 2 numerical variables. Always make sure that the necessary packages are loaded before you begin working. Part 3 will deal with 4 areas of caution that you should be aware of when you look for a relationship between 2 numerical variables. The first topic will be extrapolation. Extrapolation is estimating the value of a response variable by using its relationship with an explanatory variable whose value is outside the observed range. We'll discuss extrapolation through an example that we've seen before. This is the scatter plot and regression line describing the relationship between right hand span and height using the Penn State 1 dataset. This regression line was computed using the Penn State data, which had subjects with right hand spans in the range of 12.5 centimeters to 26 centimeters. This can be seen by looking at the range of values along the x-axis. If we tried to use this regression line to predict the height of the tallest living male, who has a right hand span of 30.48 centimeters, we would get his predicted height as 79.72 inches. He's really 99 inches tall. We've tried to use a regression line that was appropriate for individuals with right hand spans between 12.5 and 26 centimeters on a person with a right hand span that is well outside of this range. This is an example of extrapolation, and you can see how it can lead to inaccurate predictions. Our second topic will be influential observations. An observation is considered influential if it has an extreme x value. Influential observations can inflate or deflate the correlation, and they can also affect the slope of the regression line. These two scatter plots show the effect that such an observation can have. The same data is plotted in both of the scatter plots, with the only difference being the addition of the influential point shown as a blue dot in the scatter plot on the right. You can see that without the influential observation, the regression line for the scatter plot on the left has a negative slope. When the influential observation is included in the data, you can see that the slope of the regression line is now positive. So the slope of the regression line changed, and the direction of the association changed when we included the influential observation. We can explore this further with the Manipulate app called Points to Watch. So let's copy and paste this into RStudio. So we'll switch over to RStudio. There are several aspects of this plot that you are able to manipulate, one of them being the number of points in the cloud. By default, we're set at 30, so right now you have 30 points in your scatter plot. The second slider allows you to change the target correlation for the cloud. This slider is like the slider that you saw in the Very Correlation app in the last part of the slides for this chapter. Currently, the target correlation for the cloud is set at 0. Let's go ahead and change the target correlation to negative 0.5. The third slider in the Manipulate window is the y-coordinate of the selected point. So there are 2 points that you can select to include in the data of your scatter plot. A red point shown here in the middle of the cloud, or a blue point could also be selected, shown here in the upper right-hand corner of the plot window. The picker at the bottom of the Manipulate window allows you to switch back and forth between which point you want to be included with the data in your scatter plot. It's currently set to include the red point. Since we're including the red point in the scatter plot, since we've selected to include the red point in the data, in the plot window, what you see is the regression line for all of the black points in the original cloud, including the red selected point. Since we've set the target correlation for the cloud to be negative 0.5, it should make sense that the slope of the regression line is also negative. Note that this red point is not an influential observation because it doesn't have an extreme x-coordinate. In other words, the x-coordinate for this red point is right in the middle of the cloud of points in the scatter plot. If we change the y-coordinate of the selected red point, you can see how this affects the regression line. Now, the regression line for the cloud of black points, including the red point, is plotted in red, and the regression line for just the cloud of black points is plotted in black. So changing the y-coordinate of the selected point from 0 to 4 pulls the regression line up while keeping the slope about the same. If we change the y-coordinate of the selected red point to, say, negative 5, we see that it pulls the regression line down a bit while keeping the slope about the same. We'll change this back to where it was set. Okay, now suppose we select the blue point instead. The blue point is an influential observation because its x-coordinate is far outside the range of the x-coordinates of the other points in the data. Look at what the inclusion of the blue point to the data set does to the regression line. It changes our slope from negative to now positive. Changing the y-coordinate of our selected point shows how the influential observation affects the regression line. Another thing that will affect the influence of an observation like this is the number of points in the cloud. Currently we have it set at 30 points in the cloud, but suppose we increase this to, say, 150. Notice now that I haven't changed the y-coordinate, but the influence of the blue point is much less than it was when I had 30 points in the cloud. If I increase this even further, say to 200, again, the influence goes down. The more points that are in your cloud, the less effect an influential observation has on your regression line and correlation. The less points that are in your cloud, the greater effect the influential observation has. You should play around with this app some more and see how influential observations affect different situations. The third topic of discussion in this section is the difference between association and causation. Again, we'll talk about this through an example. In the M111 survey data, we observe a negative association between one's height and GPA. This can be seen by looking at the direction of the cloud of points in the scatter plot and by looking at the sign of the correlation coefficient. This negative association indicates to us that taller people have lower GPAs and shorter people have higher GPAs. But correlation does not imply causation. In other words, being tall does not cause you to have a low GPA, just as being short does not cause you to have a high GPA. In this example, there is a confounding variable at play that is at least partially responsible for the observed association. If we group the scatter plot by sex, we see that the guys are colored in pink and the girls are colored in blue. So you can see that the guys tend to be clustered around here and the girls tend to be clustered around here. By looking at the average height and GPA for the guys and comparing this to the average height and GPA for the girls, we can help to explain the negative association we see in the scatter plot overall. The average height for the guys is higher than the average height for the girls. On the other hand, the average GPA for the guys is lower than the average GPA for the girls. The girls are clustered here on the left. They have a lower average height and a higher average GPA. The guys are clustered here on the right. with a higher average height and a lower average GPA. This is what's giving us an overall negative association between height and GPA. This can be seen even further by comparing the correlation coefficient of the aggregate data to the correlation coefficients for the subgroups, guys and girls. Overall, we saw that the correlation coefficient was negative for the aggregate data. However, the correlation coefficient for just the guys is positive, and the correlation coefficient for just the girls is also positive. This is actually an example of Simpson's paradox, which is our last topic of discussion in this chapter. We saw Simpson's paradox back in Chapter 3. It occurs when the direction of the relationship is one way when you look at the aggregate data, but turns out the opposite way when the data is broken into subgroups based on some third lurking variable. This is what we saw in the prior example. We had a negative association between height and GPA when we looked at the data on the whole. However, when we broke it down by subgroup, for the guys subgroup, we had a positive association between height and GPA. For the girls subgroup, we also had a positive association between height and GPA. We stated this in terms of variables back in Chapter 3. X was our explanatory variable, Y was the response, and Z was the third lurking variable. We said that Simpson's paradox occurs when a relationship between X and Y reverses its direction when the data is broken down by the values of the variable Z. Let's look at one more example of this. You should load, view, and run the help file on the dataset SAT. We will see an example of Simpson's paradox when we set out to answer the research question, how is annual teacher salary related to student performance on the SAT? Here we'll treat salary as the explanatory variable, so in other words, X is salary. And we'll treat SAT as the response variable, so in other words, Y is SAT. Salary is a numerical variable that represents a state's average annual teacher salary. SAT is also a numerical variable that represents a state's average cumulative SAT score. When we look at the aggregate data to observe the relationship between annual teacher salary and cumulative SAT score, we see that we have a negative association between these variables. In other words, it appears that states that pay their teachers more have lower average SAT scores. How is this possible? The lurking variable at play here is the variable frac. Frac is the percentage of students in the state who take the SAT. We'll investigate what happens when we take this variable into account by running the following manipulate app, dtrelscat. So let's copy and paste this code into RStudio. Here we see a scatter plot of the aggregate data where salary is the explanatory and SAT is the response variable. The points that are highlighted in red now represent those states where 4% to 9% of the students take the SAT. We're able to manipulate this interval for frac by changing the center of it or changing the bandwidth of it. We can also show the regression lines, and you can opt to output the regression analysis as well. By showing the regression lines, we see the regression line for the aggregate data is plotted in black. The regression line for only that subgroup of states where frac is between 4 and 9 is plotted as a red dashed line. So here you can see the association between salary and SAT for the aggregate data is a negative association. However, when we subgroup and only pull those states where the value of frac is between 4 and 9, we can see that the relationship between salary and SAT is a positive association. We can move this subgroup along. So now we have just those states highlighted where the percentage of students who take the SAT is between 8% and 11%, And again, for this subgroup, you can see that the relationship between salary and SAT is a positive association. As we move frac along, it appears that for almost every subgroup that we see, we're getting a positive association between salary and SAT. However, the association between these variables is negative when we look at the aggregate data. We've identified the lurking variable frac, and we've seen that when we break the data down by subgroups based on the value of frac, the direction of the association between SAT and salary reverses. This is an example of Simpson's paradox. So how do we explain it? We first want to study the relationship between X and Z. In other words, we want to study the relationship between frac and salary. When we plot this scatter plot, we see that there's a positive association between frac and salary. States with a high percentage of their students taking SAT are states where education is a high priority. Those states also tend to pay their teachers more money. Our second observation is made by comparing the third variable to the response variable. In other words, we should now compare frac to SAT. When we plot this scatter plot, we see a negative association between these variables. States where a large proportion of the students take the SAT, the test takers make up a broad pool of abilities. This broad range of abilities causes the average SAT score to be lower. In states with a low percentage of students taking the SAT, the pool of test takers is a more elite group. In other words, it's only those students who are college-bound, highly motivated, studious individuals. This pool of test takers has a higher average SAT score. So we've observed a positive association between salary and frac. We've also observed a negative association between frac and SAT. So putting this all together, we end up with the negative association we saw in the aggregate data between salary and SAT. In other words, states where education is a priority pay their teachers well, but they handicap themselves by encouraging most students to take the SAT. This is what gives us the negative association between salary and SAT. This is the end of Chapter 4. Thank you for watching.